This video is going to look at the work done by an applied force lifting or lowering an object against the force of gravity. In these first examples, we're going to look at something that starts from rest, moves some vertical distance d, and then stops. In those cases, if it starts from rest, moves, and then stops, the net work done on the object must be zero. The initial kinetic energy of the object is zero. The final kinetic energy of the object is zero. And so since the net work is the change in kinetic energy, the net work done on the object must be zero. It doesn't mean that there aren't any forces doing work. It means that the total work done is zero. In this case, we have two forces that are doing work. We have the work done by the applied force lifting the object, and we have the work done by gravity. The work done by gravity, as we talked about in the last video, the work done by gravity lifting something a distance d is negative mg times the vertical distance d. The work done by gravity when you're lifting something is negative because the motion is upwards, the force of gravity is downwards, so it's taking energy away from the object. It's doing negative work. If the net work done is zero, then the work done by the applied force, the force that's lifting the object, must be the exact opposite of the work done by gravity. So the work done by the applied force will have to be positive mgd. So the total work done, positive mgd plus negative mgd, that total work done is zero. Again, the work done by the applied force lifting the object is positive because the force that's lifting it is in the same direction that the object is moving. Again, this was specifically for the case where something starts at rest, moves, and then stops, where the net work done is zero. This same reasoning would be for something that's being lifted at a constant velocity. If you're told that something is being lifted at a constant velocity, again, the kinetic energy is not changing, and so the work done by the applied force lifting it and the work done by gravity would be the opposite of each other as well. For something that's moving downwards, the force of gravity is in the same direction as the motion, so the work done by gravity is positive. Again, if we're talking about an object that starts from rest, moves a vertical distance d, and then stops, so starting from rest, moving, and stopping, the change in kinetic energy is still zero. And so if the work done by gravity is positive mg times the vertical distance, then the work done by the applied force has to be the opposite of that. So the work done by the applied force would be negative mg times the vertical distance. The work done by the applied force lowering the object is negative. Gravity is trying to add energy to it, it's trying to speed it up. The applied force has to pull against that motion, trying to slow the object down to keep it from crashing into the ground. Again, this is specifically for the case where it starts at rest, moves, and then stops. Or again, this same reasoning would apply to something that's moving, that's being lowered at a constant speed. So let's look at an example. We have an initially stationary 15 kilogram crate of cheese wheels, and it's pulled by a cable a distance of 5.7 meters up a ramp. So the distance along the ramp is 5.7 meters, and it's lifted to a height of 2.5 meters. So it's lifted a vertical distance of 2.5 meters where it stops. Again, we can see that this is the situation that we were just talking about. This is something that starts at rest, it moves, and then it stops. And so because it starts from rest and it ends at rest, the change in kinetic energy is zero, so the net work done is going to be zero. Again, initially stationary means the initial kinetic energy is zero, it moves, and then it stops, so the final kinetic energy is zero. The change in kinetic energy is zero, which means that the net work done on the object is zero. So let's look at the work done by the individual forces. Finding the work done by the force of gravity as it is lifted along the ramp. Again, the work done by the force of gravity in this case is going to be negative. The force of gravity is downward, it's moving upward. So the work done by gravity is going to be negative. It's going to be the force of gravity, 15 kilograms times 9.8 meters per second squared, times the vertical distance it moves, 2.5 meters. Again, the 5.7 meters along the incline we don't need to worry about. All we need to know to find the work done by the force of gravity is the vertical distance that it moves. We were told that it moved a vertical distance of 2.5 meters. So the work done by the gravitational force is negative 367.5 joules. Again, that work done is negative because the force of gravity and the motion of the object are in opposite directions. The force of gravity is downward, the object was moving upwards, so the work done by the force of gravity must be negative. Now looking at the work done by the tension in the rope, we know that the net work done is 0, so the work done by gravity plus the work done by the tension in the rope plus the work done by the normal force would have to add up to equal 0. In this problem, because it's sliding along the ramp, the work done by the normal force is going to be 0. The normal force is perpendicular to the motion. And so the work done by gravity and the work done by the tension are going to be opposites of each other. We just calculated the work done by gravity. The work done by gravity was negative 367.5 joules. So the work done by the tension in the rope must be positive 367.5 joules. Again, we didn't need to know anything about the angle. We could have found the angle because we knew the hypotenuse and we knew the vertical distance. But we didn't need to do anything with the angle to find the work done by the tension. If we were looking for what the tension in the rope was, we could use this work done by the tension. The tension in the rope was pulling parallel to the ramp. It moved a distance of 5.7 meters parallel to the ramp. And so the tension times 5.7 meters would have to equal that 367.5 joules. And so this tells us that the tension in the rope is 64.47 newtons. Here we have a conceptual question with two identical boxes being pushed up frictionless inclines. Both of the inclines have a height of 10 meters. One of them, the angle is 70 degrees, one of the angles is 10 degrees. And so we're sliding the box up the ramp at a constant velocity by pushing parallel to the ramp. So this is another case where the change in kinetic energy is 0. We're moving it and we're moving it at a constant velocity. And we want to compare the force needed in each of the cases. In both cases, the work done by that force must be the same. The work done by that force must be the opposite of the work done by gravity. The work done by gravity is negative mg times the vertical distance, so the work done by the force is positive mg times the vertical distance. In the first case, the box moves a distance L1. In the second case, the box moves a distance L2. L2 is greater than L1, so even though we have that the work done is the same, the force, which is acting, in both cases it's acting parallel to the ramp, the force acts over a longer distance in case B. And so the applied force in case B, the 10-degree incline, that applied force is smaller than it is in case A. The work is the same, but since the distance along the ramp is bigger in the second case, the force must be bigger in case A. This is an example of a simple machine. An inclined plane is a simple machine. You're getting the same work done, but the force that you need to do that work is different. With a gentler incline, it doesn't mean that you have to do less work to move a vertical distance of 10 meters, but the force that you need to apply to move up that incline is smaller. The situations we've been talking about in the past couple of slides have been things that have started at rest, moved, and then stopped, or things that were moving at a constant velocity. But that's not always the case. So this next problem is going to be something that is accelerating. We have an elevator cab with a mass of 500 kilograms. It's initially moving downward at 4 meters per second, and the cable begins to slip. And so it has a downward acceleration of g over 5. As it falls down a vertical distance of 12 meters, we want to calculate the work done by the gravitational force. The work done by the force of gravity is going to be positive because the gravitational force is downward, it's moving downward, and it's the force of gravity mg times the vertical distance d. The force of gravity is 500 kilograms times 9.8 meters per second squared. The vertical distance is 12 meters. So the work done by the force of gravity is positive 58,800 joules. Again, that was 500 times 9.8 times 12, so 58,800 joules. So as this is moving downward, the force of gravity is adding 58,800 joules of energy to the object. Now let's look at the work done by the tension in the elevator cable. This is not a case where the work done by the tension is going to be the opposite of the work done by gravity. This is accelerating downward, and so it's gaining kinetic energy. The work done by the tension in the cable is going to have to be less than the work done by gravity. To be able to calculate this work done by the tension in the cable, we need to first figure out what the tension in the cable is. This is something that involves Newton's second law. We have the tension pulling up, we have the force of gravity pulling down, and we know that together those two forces are causing an acceleration of g over 5, or 9.8 meters per second squared over 5. So the net force is the force of gravity mg minus the tension t. We're calling down positive in this situation. We're calling the direction of the acceleration positive. So net force is the individual forces added together, mg minus t. Net force, by Newton's second law, is also mass times acceleration. So it's the mass times the acceleration of g over 5. Again, we're calling down the direction of the acceleration as positive. So putting those two together, I can solve for the tension. mg minus the tension has to equal m times g over 5. And so the tension has to equal 4/5 mg, or 4/5 of 500 kilograms times 9.8 meters per second squared, or 3,920 newtons. So now that we know the tension in the cable, we can figure out what the work done by that tension is. The work done by the tension in the cable is going to be negative, because the force of the cable is upwards, the motion is downwards. It's the force, 3,920 newtons, times the vertical distance of 12 meters. So the work done by the tension in the cable is negative 47,040 joules. Again, the work done by gravity was positive. It was adding kinetic energy to the object. The work done by the tension in the cable was negative. It was trying to take kinetic energy away from the object. But the amount of positive work done by gravity and the amount of negative work done by the tension in the cable do not add up to equal 0. So if we wanted to look at that net work that's done, the net work would equal the work done by gravity plus the work done by the tension. So that's positive 58,800 joules plus negative 47,040 joules. So the net work done on the cab is positive 11,760 joules. Again, this goes along with the fact that we know that this object was speeding up. As this elevator was falling, it was moving downward, it was accelerating downward. If the acceleration and the motion are in the same direction, then the object is speeding up. And so if this object is speeding up, it's gaining kinetic energy, the net work done on the object must be positive. And if we wanted to calculate the kinetic energy that it has at the end of the 12 meters, again, this is something where we could have used kinematics. There's a constant acceleration, and so we could go through and find what the speed is from that. But looking at this from a work and energy point of view, the net work done is positive 11,760 joules. That net work done has to equal the change in kinetic energy. Positive 11,760 joules equals the final kinetic energy minus the initial kinetic energy. Again, it's not starting from rest. We were told that the elevator cab was moving at 4 meters per second. So the initial kinetic energy is 1/2 times 500 kilograms times 4 meters per second, that quantity squared. This gives us a final kinetic energy of 15,760 joules. So it started with a certain amount of kinetic energy. We added kinetic energy to it. Again, gravity added some kinetic energy. The tension took away some kinetic energy. Overall, there was a net addition of kinetic energy. The net work was positive. And so it gave us the final kinetic energy. Sometimes instead of what is the final kinetic energy, we're asked what is the final speed. And so this is something where we could just use the definition of kinetic energy. Kinetic energy is 1/2 mv squared. So if we set that final kinetic energy, 15,760 joules, equal to 1/2 times 500 kilograms times v squared, this would give us that the speed of the elevator cab is 7.94 meters per second after it has fallen 12 meters. Again, we said that it sped up, so it started at 4 meters per second and it sped up to 7.94 meters per second after falling the 12 meters.